In today's math lesson, we are going to factor out a monomial. Using the previous lesson as a guide, after you find the greatest common factor, determine what is left over from each term. When you do the greatest common factor, you might actually have nothing left over. And if nothing is left over, then you show that location. You show that there had been a term there with a 1. So to show just a simple example, if you had a term plus another term, who knows what they are? You will find their greatest common factor, and then in parentheses, you will say, so what's left over from the first term? It goes there. And then what if you have a plus or a minus here in the middle between the two terms, you'll have that same symbol here. And then whatever was left over from their second term that didn't make it into the greatest common factor, that will be acknowledged here at the back end of your parentheses. Here in example 1, let's factor these two terms using their greatest common factor. So let's find the greatest common factor first. 3x squared comes from 3 times 1 times x, while 6x, and you want to break this all the way down into just primes, comes from 3 times 2 times x. We now see that between these two terms, the greatest common factor is 3x. So that's not new. We did that in the previous lesson. So the new part is determining what's left over. So you open with a set of parentheses, and you say, for my first term of 3x squared, what didn't make it into the greatest common factor? A 1 and an x. Well, 1 times x is just x. There's that. There is a plus in between our two terms here in the initial problem, so I put a plus after my x. And then I look at my second term, the 6x, and I say, okay, so what didn't make it into its greatest common factor? The 2. So the 2 is what comes after my plus sign. Close it out with my parentheses. And there you go. We have factored our first polynomial. In our second example, we are going to, again, factor our polynomial of two terms using the greatest common factor. Looking at our first term, 10j squared, what is 10 broken down into its prime numbers? That's 5 times 2. J squared comes from j times j. 6j, again broken down into its prime factors, is 2 times 3, and a j. We see here that the two terms have a greatest common factor of 2j. And just like we said in the previous lesson, this coefficient of 2 does not have to be vertically written right above itself from row to row. As long as it is present, then it can be used. Now let's look to see what's left over. So from my first term of 10j squared, we see that there's a 5 and a j that was left over. Between our two original terms, there is a minus, so we place a minus in our answer. And then looking at 6j, our second term, we say what was left over from the greatest common factor? A 3. And so we close that out with a set of parentheses, and there you go. In our third example, we're going to factor out our two terms, again using the greatest common factor. Our first term, 3z cubed, comes from 3 times 1 times z times z times z, while our second term of 9z squared, we have to break the 9 into its prime factors, comes from 3 times 3 and z times z. We see from our factorings that between these two terms, we have a greatest common factor of 3 and 2 z's. So we write that as 3z squared. Now let's look to see what's left over. In our first term, I have a 1 and a z. And since it's 1 times z, I don't have to show the 1. It is a z. Between our two original terms, there was a plus sign, so I now have a plus sign after my z. And from my second term, I didn't use one of my factors of 3. So I place it here after the plus sign, close it off with a set of parentheses, and there you go. In example 4, let's again factor out our two terms using the greatest common factor. I adjusted this problem slightly, and you'll find out why in just a moment. Let's break down 64m cubed. So remembering that we want to work with primes. 64, sure, it comes from 8 times 8. But where does 8 come from? 8 comes from 2 times 4. Well, 2 is prime, but 4 is not. So 4 comes from 2 times 2. And then we said it was 8 times 8. 2 times 2 times 2 makes 8. And we have another set of 2's for that second 8. All right. So the first 3 2's came from the first 8. The second 3 2's came from the second 8. And as the case would be, I have an m cubed. So let's acknowledge all 3 of those m's. Down here below, I have an 8m. And as we discovered just a few seconds ago, 8 comes from 2 times 4, and 4 comes from 2 times 2. And there's our m to go with it. There's quite a bit happening in this problem now. I have 3 bundles of 2's. So what does that do for us? It tells us that we have 2 times 2 times 2 and a bundle of m's. We also see from up here the dissection of our first term that I have 3 remaining 2's and 2 m's. So we'll shorthand that with an m squared. And there's a minus between these two terms. Now there is nothing left over from our second term of 8m. And we said in the introduction that if everything gets used in the greatest common factor from a term, then you acknowledge that there had been a term there by placing a 1. Let's clean this up. Time for our final answer. 2 times 2 times 2. Well, that's 8. And an m right there beside it. Open your set of parentheses. 2 times 2 times 2 is another 8 with an m squared minus 1. Close your parentheses. This is our final answer, having adjusted our original problem so that we had 64m cubed minus 8m, and we are able to show lots of bundles and an entire term was used in the greatest common factor. There you go. In our fifth and final example, let's factor out these two terms using their greatest common factor. Our first term of 13r cubed. Well, 13 is prime all by itself, so that's just 3 times 1. And I have an r cubed, so that's 3 r's. 9t squared, our second term, well, 9 comes from 3 times 3, and t squared comes from t times t. What do these two terms have in common? A whole lot of nothing. Yes, technically, you can absolutely say that this second term is multiplied by 1. That's true. But there is nothing here to speak of that is obvious and of value when multiplying. So when there is nothing in common, we just rewrite the original problem because it already is as simplified, as factored as it could possibly be with nothing to change. There you go.